in both physics and mathematics from Stanford University, a Master's of Advanced Studies in Theoretical Physics from the University of Cambridge, and PhD in Physics from Harvard University. He was subsequently a postdoctoral scholar at UC Davis at the Center of Quantum Mathematics and Physics, and now a Hayden Simon Fellow at Caltech. His research interest is focused on application of quantum information theory to high energy physics, as well as studying the infrared sector of quantum field theories and quantum gravity in an effort to make connections with observations. Let us all welcome our speaker.
Yeah, thank you very much for the introduction. So I'm going to share screen now. And okay. So actually, I can't see you guys. Can you guys see the screen?
Yes.
Okay, so yeah, I can't see anyone. Like it's just a white icon. Yeah, I mean, so if you guys have questions, just I guess speak up and feel free to interrupt me at any point in time. Does that work?
Yes.
Okay. Okay, great. So yeah, so thank you very much for the introduction. Today I will be talking about marginal independence and an approximation to strong subadditivity. Okay, so this is done in collaboration with Veronica Hubini and Max Rota. And the primary focus will be this paper that came out in November. And so the goal of the presentation today is the following. So I will introduce this object called the subadditivity cone. And it's basically a convex region in entropy space that satisfies all instances of subadditivity involving n subsystems. So you can think of this as some number of qubits. And so what is the entropy space? So here I have an example of entropy space involving 2 qubits. So say qubit A and qubit B. So it's a vector space. And so given every point in this vector space, it's specified by its value on the 3 axes, which tells me the entropy of A, the entropy of B, and the entropy of AB. So, I will give a much more comprehensive introduction to what the entropy space and the subadditivity cone later. But this is the picture that you have in mind. Essentially, it's telling you what is the entropy of a given quantum state. Then I will try to connect this entropy space to the theory of lattices. So a lattice in mathematics is a partially ordered set or pole set where every 2 elements, it has a meet or a greatest lower bound and a join or a least upper bound. So I mean, definitely before doing this project, I was not very familiar with lattices. So I would be perfectly happy if all you got out of this talk is just to have a sort of a intuition for what are lattices, why they could be interesting. So I'm much more happy to not get through all my slides and make sure you guys understand the things that I'm saying than for me just to fly through everything. So again, please ask questions whenever something is unclear. The point, though, is that we would like to study the subadditivity cone using lattice theory for, in particular, let's do it for n equals 3 first, so 3 qubits. And then we're going to prove numerous structural results about what are the properties of this lattice. And of course, if we only did this for n equals 3, it will be a very limited result. But what we will do is we will generalize all these structural results to arbitrarily large number of parties. So that's the goal of the presentation. And in particular, we're going to see why it is so difficult to study entropy cones for n greater than or equal to 4. So 4 qubits or more. So what is the motivation for this? My training is as a high energy theorist. And the reason why we're interested in this is because this will constrain the holographic entropy cone, which is the set of entropy vectors that are realizable by holographic states and lie inside the subadditivity cone. So if these words don't make sense to you, don't worry about it. Essentially, high energy theorists were interested in these special states, special quantum states called holographic states, because we know how to compute entanglement entropy for quantum field theories involving them very easily using the ADS CFT correspondence. And the hope, so basically, all I'm saying is that from a higher energy perspective, we're interested in essentially constraining what the holographic entropy cone is. And so this work that I will be telling you today about will be able to help take us a small step towards that direction. From a quantum information theory standpoint, which may be what you guys are more interested in, the reason that this is interesting is because it's a step towards solving the quantum marginal independence problem, which is very easy to state. All it's saying is, suppose I hand you a bunch of qubits, and I'm just telling you, okay, so I want a subset of these qubits to have correlation with this other subset, but I also don't want correlation between, this different subset of qubits with this other different subset. And I specify this for all pairs of subsets. The question is there a quantum state that realizes this pattern? And so what we're going to try to do is try to take a step towards answering this question. And the way that we are able to make quite a bit of progress or try to understand the structure of like how these patterns behave is through the lattice theory. So what is the roadmap for today? So we're going to begin by reviewing what the entropy cone is and what are patterns of marginal independence. Then I will introduce a very natural ordering for the mutual instances of mutual information, and we're going to call this set the mutual information poset. We're going to introduce a condition called Klein's condition as an approximation to strong subadditivity, because at the end of the day, even after we impose subadditivity, we want not all of these states in the subadditivity cone will be realizable by quantum states because they might violate strong subadditivity. And we're not going to impose strong subadditivity, but we're going to approximately impose it by using this Klein's condition that I will explain quite a bit more about. And finally, we're going to then introduce the various lattices that are associated with the subadditivity cone. And in particular, we're going to focus on the n equals 3 for 3 qubits. And then we're going to extend our results to arbitrary n for n greater than or equal to 4. So this is where the roadmap of where we're going. Are there any questions?
No, I'm good. Thank you.
OK, great. OK. So let's begin with something simple. So what are the entropy inequalities? So if you hand me a density matrix rho involving n subsystems or qubits, we can associate to it an entropy vector S of rho, where S of rho lives in a 2 to the n minus 1 dimensional vector space. So suppose I hand you 2 qubits, A and B, then I can specify the entropies configuration of these 2 qubits by telling you what is the entropy of qubit A, entropy of B, and entropy of AB. So there's 3, so 2 to the 2 squared minus 1 is 3. If I have 3 qubits, then it will be in a 7-dimensional vector space because I will be the entropy of A, B, C, AB, BC, AC, and then ABC. So naturally, you might wonder, well, are all entropy vectors in entropy space realizable by quantum states? And the answer is, of course, not, because we all know that entropies have to be positive. So this very simple positivity of entropy already confines us to the positive region of entropy space. I cannot have any components of the entropy vector be negative. But on top of that, there are also many inequalities that quantum states have to satisfy. So for instance, they have to satisfy subadditivity, Araki-Lieb, strong subadditivity, weak monotonicity, just to list a few. So in addition to just staying inside the positive region of entropy space, what happens is that it has to the entropy vector is realizable by a quantum state only if it lives in a subregion of this positive region in entropy space. So here, I, J, and K, these subscripts, we're using them to label various subsets of the parties. And so if, for instance, if I impose just these linear inequalities, so what ends up what these inequalities carve out is a polyhedral cone that is in entropy space. And so only vectors inside this cone are realizable by quantum states. Okay, now let's use purification symmetry. So if you hand me parties 1 through n, we can introduce a purifier, which we will call 0 or O, such that the composite system, including the purifier, is a pure state. So the entropy of this composite system is equal to 0. Once we introduce this pure state, then this obeys this very nice property where the entropy of some subset of parties is equal to precisely its complement, where now I'm underlying the subscript to indicate that we can include the purifier as a subsystem. Now, once we introduce purification symmetry, we can then write arXiv and weak monotonicity that I had on the previous slide as just SA or SSA involving the purifier. So instead of working with 4 inequalities, actually, we just need to specify 2 inequalities, where now these indices can include the purifier. So, okay, so what is a quantum entropy cone? The quantum entropy cone is the region of entropy space such that every entropy vector in it is satisfied by some quantum state. You hand me a vector, entropy vector, it tells me the entropies of various, all its various subsystems. And then I can construct a density matrix such that when I do partial traces, I can recover all the numerical values of the von Neumann entropy. This means that it must be contained in the spaces that are carved out by the entropy inequality. So the quantum entropy cone must be in the positive region that is constrained by all the entropy inequalities. So for n equals 2 and n equals 3, if I have only 2 parties or 3 parties, it is known that the inequalities SA and SSA, including the purifier, completely specify the cone. This means that every single vector inside the cone that is specified by SA and SSA, there exists a quantum state that can realize the entropy of the entropy vector. Unfortunately, this is not known for larger n. So let's now introduce mutual information because mutual information will be the star player in the game. So mutual information, what it does, it measures correlation between 2 pairs of subsets of subsystems. So for instance, suppose I have some collection of subsystems I and some collection of subsystems K. The mutual information, as I'm sure you guys are very familiar, it's S of I plus S of K minus S of IK. And what it does is it measures correlation. It vanishes if only if the 2 subsystems factorize, in which case there is no correlation between the 2 subsystems. And if there's correlation between the 2 subsystems, if there is entanglement, then the mutual information will be positive. So now suppose I have some collection of qubits, and I can indicate the mutual information between all the various pairs of subsystems. I can then consider the following bipartition. So let E0 indicates the collection of mutual informations that are vanishing. So for instance, like I can say, the mutual information between A and BC is equal to 0, between B and C is equal to 0, between C and D is equal to 0. So all these pairs of subsystems, they have no correlation between them, and those are the mutual informations I put into E0. And E star is everything else. So these are the mutual informations that have positive MI. We can then define a pattern of marginal independence to be any such bipartition. So each PMI specifies a pattern of correlation between the various subsystems. And the pattern and the quantum marginal independence problem asks what are the bipartitions that are realizable by quantum states. So this is a very simple question to state. It's a much more coarse-grained question than saying what are the realizable entropy vectors, because I'm not saying what are the numerical values of the mutual information. I'm just simply saying all I require is some of these mutual informations to vanish and everything, all the other mutual information to be positive. And does there exist a quantum state that satisfies these conditions? So a moment's thought will clearly tell you that not all PMIs are realizable. So as a simple example, consider the following. So we have, let's consider 3 parties, for instance. So I want the mutual information between A and B, between B and C, and between A, B, and C to equal 0. So I don't want correlation between these 3 pairs of parties. But I do want correlation between A and BC. Now, why isn't this realizable? It's because of this following linear dependence. So if I take, you can check that this linear dependence, that this identity is satisfied. And what we're saying is we want the first 3 terms in this equality to equal 0, which will automatically force the mutual information between A and BC to equal 0 as well. So in this sense, this pattern is not realizable because of a linear dependence. So how do we come up with a description for PMIs that take this linear dependence into account? So what we do is we adopt a geometric description. So each MI instance I of j colon k equals 0. Each instance of MI, it denotes a hyperplane. And the collection of all such hyperplanes is typically in mathematics literature, they call it a hyperplane arrangement. And so here we call it the MI hyperplane arrangement, or the MIA for short. The intersection of the various hyperplanes, they are called flats. And so now what we're saying is that PMIs, these patterns of marginal independence, they have to be flats in the MIA. So why does this bypass the problem that I stated in the previous slide? Because now if we embrace this geometric description for what the PMIs are, then the hyperplane that is at the intersection of A colon, the mutual information of A, B, B, C, and A, B, and C equals 0. This is the intersection of 3 different hyperplanes. And if we look at the MIA, this will automatically lie on the hyperplane A colon BC is equal to 0 as well. So the pattern that we stated in the previous slide, it would never arise from this hyperplane arrangement, because there just simply doesn't exist a flat where these 3 are 0 and this is positive. So this automatically takes into account linear dependence. However, not all flats are PMIs, at least they're not realizable. Some flats, they violate subadditivity. So to see what I mean by that, consider again this relationship, this linear dependence. Now suppose all I want is I want the mutual information between A and B and A, B, and C to equal 0. So I don't want correlations between A and B and A, B, and C. But I want positive correlations with all the other subsystems. Then this is disallowed because setting these 2 equal to 0, from this relationship, we can see that these first 2 terms are 0, but mutual information is non-negative by subadditivity. So this will automatically force this MI and this MI to equal 0 as well. And so again, this is disallowed. So there exists no quantum state that will satisfy this PMI because of subadditivity. And this is where we define the subadditivity cone, because we want to take into account both linear dependence and these subadditivity constraints. So the subadditivity cone is defined to be the intersection of all half spaces specified by subadditivity. the PMI can then be defined to be simply the linear span of all the faces of the subadditivity cone. So because the PMIs, they are subspaces, they cannot just be specified by the faces of the subadditivity cone itself, because the faces are semi-infinite regions of the linear of the vector space. So what we need to do is they are actually the linear spans of the faces. So that's a minor technical detail. So there are two important classes of faces in the for these subadditivity cones, or any polyhedral cones for that matter. There are the one-dimensional faces, which are the extreme rays. So the one-dimensional faces, these are the sort of, if you think of a three-dimensional polyhedral cone, these are the rays that generate the cone. And every point inside the cone is a positive linear combination of these extreme rays. There's also the facets, which are the d-1 dimensional faces. So these are, like, again, if you have the picture of a three-dimensional polyhedral cone in mind, the faces are just the two-dimensional planes that sort of carve out the cone. And usually we define the entire cone to be called a d-dimensional face. That's the typical convention. So after doing all this work, the question is, okay, well, now are all the flats that are linear spans of the subadditivity cone faces, are they all realizable? And of course, the answer is still no, because these PMIs, they might violate an instance of strong subadditivity. We have not included the strong subadditivity condition in our analysis yet. So then, of course, then you can say, well, can we just simply continue doing what we have already done? So previously, to impose subadditivity, we started looking at the cone that's carved out by all the instances of SA. Now we can say, well, if we want to impose SSA, we just include all the inequalities, include SSA, and carve out a even more complicated entropy cone. And there's two reasons that we don't want to do that. The first reason is because if we do that, then we have to include so many more inequalities into our analysis. So say, like, if we are considering like 5 or 6 parties, the number of strong subadditivities, it's going to be like, there's just going to be like exponentially more number of inequalities we have to take into account. And so from a computational standpoint, that's very inefficient. The second reason that we don't want to do this is because the pattern of marginal independence, it's only a statement about mutual information. And so it's only sensitive to subadditivity. If we carve out a new entropy cone using strong subadditivity, then there's going to be many different faces of the SSA cone that correspond to exactly the same PMI. So we're actually fine-graining the problem much more than we really need to. And it is for this reason that we're going to, instead of just analyzing a new cone, entropy cone involving SSA, we're going to formulate a slightly weaker constraint called a Klein's condition that we'll now introduce. And it will be an approximation to a strong subadditivity, but it can be formulated completely combinatorically without introducing any new inequalities. And I will show, like, essentially how lattices come into play. So this is probably a good point to ask. Are there any questions so far? Okay, so let me introduce. Oh, sorry.
No, I'm good. I'm okay up to this point. Thank you.
Okay, great. Okay, so let me then introduce Klein's condition. So Klein's condition is the following. So I'll just state it first. So suppose I tell you that the mutual information between I and J union K is equal to 0. Then Klein's condition is simply the condition that this will automatically imply that the mutual information between I and J is equal to 0, and I and k is equal to 0. And the reason that we call this Klein's condition is because this implication arises from our application of Klein's inequality. So the reason this is an approximation of SSA is because we can rewrite SSA in as a difference of two mutual informations. And if I write it in this way, then you can see automatically that SSA implies Klein's condition, because if I set the first term here is equal to 0, then immediately this would imply that I of I colon k is equal to 0 as well. And of course, this is symmetric under exchanges between j and k. Therefore, we're going to define a PMI, and we're going to call it say that it satisfies Klein's condition, or that it's Casey compatible, if it has this property, which is that if the mutual information between j prime and k prime is equal to 0 in the PMI, this also implies in the PMI that the mutual information between j and k is equal to 0 for all subsets j and k of j prime and k prime. Now, this condition here then naturally leads us to introduce ordering for the collection of mutual informations. So a partially ordered set, a poset, is a set P with some partial order specified by this less than or equal to sign that I have here. And the collection of mutual information, it naturally forms a poset. So the partial order is the natural one that I just alluded to in the previous slide. I say that this mutual information between I and k is less than or equal to that between I prime and k prime, if I is a subset of I prime and k is a subset of k prime, or I just exchange I and k. So for fixed n, the MI poset has cardinality it has cardinality that is given by the Stirling number of the second kind of n plus 2, 3. So for n is equal to 2, there are 6 mutual informations. For n equals 3, there are 25 mutual informations, and it grows very quickly from there. So far everything I'm saying is very abstract. So let's look at some concrete examples just to ground ourselves. So let's look at the n equals 2 example. So the poset structure of the is oftentimes captured very cleanly, at least for posets of relatively few number of elements via a Haas diagram. So the Haas diagram is drawn as follows. So here, first of all, I write down the elements in the set, and I sort of order them like the elements that are like higher tend to be elements that are like larger, and the elements that are lower are the elements that are smaller. And I draw a line between two elements if, say, this element is bigger than this element, and there's no element in between these two elements. So for instance, I of a colon BO is greater than or equal to I of a colon B, and it's also greater than I of a colon O. This is the ordering that I talked about in the previous slide. And there's a natural notion in order theory called a down set. And a down set is a subset of the poset where if X belongs to the subset, then every element that is less than or equal to X also belongs to that subset. And if the subset has this property, then it is called a down set. So for instance, suppose I say that I of a colon BO is in a down set. Then this down set has to include this element, but also the elements less than or equal to it. So it has to include this element and this element. Similarly, if I include, say, the down set includes this element and this element, then it has to include both of these elements, but also all the elements less than or equal to them, which would be all the bottom elements. So then we can reformulate what we mean by a PMI to be Casey compatible. It is Casey compatible if and only if its set of vanishing MI instances form a down set. Okay, so now let's move on to lattices. So the reason why we want to look at lattices instead of just posets, because lattices are posets with a lot more structure, And over the last century, mathematicians are able to exploit a lot of the structure to prove various properties about these lattices. And we're hoping to essentially import a lot of those results from the mathematical literature into the analysis that we're currently doing. So a poset is a lattice if any two elements, so any two elements in the poset have both a join, which we typically write as this big V, which is a least upper bound, and a meet, which is this big wedge, or greatest lower bound. So you may say, okay, well, is the MI poset a lattice? Well, immediately, so there's two reasons why the MI poset is not a lattice. The first reason is very trivial. It's not a lattice because there's no top element nor a bottom element. So let's look at the n equals 2 Haas diagram here again, just for illustration purposes. So if I take this element and this element, I say, well, what is its join? What is its least upper bound? Well, there is no least upper bound because there's no elements that are greater than or equal to these two, or any pair of these largest elements. Similarly, any of the pair of these bottom elements, they do not have a meet because there isn't greatest lower bound between any of these two bottom elements. So this is easily fixed because for n equals 2, all we need to do is just add a formal element. So we just add an element here, and then we connect lines here. And then this is what we call a top element. And similarly, we can add an element that's less than all three of these bottom elements. And then this is what we call a bottom. So once we add this formal top element and bottom element to the n equals 2 MI poset, then it becomes a lattice. But unfortunately, for n greater than 2, the MI poset still is not a lattice, even if we include this formal top and bottom element. To see why, here I drew a subset of the n equals 3 MI poset. And the reason it's not a lattice is, suppose I want to compute the meet of these two red elements. So I want to find what is its greatest lower bound. If you do this, you'll notice that both of these blue elements qualify to be its greatest lower bound, because this element is less than or equal to this element. It's also less than or equal to this element. And similarly, I of B colon C is less than this element, and is also less than this element. So both of these elements, there is no greatest lower bound for these two elements. And similarly, if you try to take the join of these two elements, you will see that either of these red elements qualify to be its least upper bound. And so the MI poset, as we've defined it, simply does not have a meet or a join for n greater than or equal to 3. And so these are not lattices in general. Okay, so what are lattices then? What are some lattices that we can study? So one thing that forms a lattice is the set of faces of the SA cone. So they form a lattice. We can order them by either inclusion or reverse inclusion. But for our purposes, it actually makes a lot more sense, and I will explain why shortly, to order them by reverse inclusion. By this ordering by reverse inclusion, then we say that the join of two faces is simply the largest face contained in both. So the join of two faces is given by the intersection of the two faces, and the meet of the two faces is given by the smallest face containing both. So as I go up in the lattice, the dimensionality becomes smaller, and if I go down in the lattice, the dimensionality becomes larger. And the reason for that is we're ordering by reverse inclusion. Thus, the bottom element is a full subadditivity cone because the bottom element contains all the faces, and the top element is the face of the smallest dimensionality. It's the one that is contained in all the faces of the SA cone, and that is just the origin. So, okay, let's again look at a very concrete example. This is not a entropy cone, but this is just a polyhedral cone that I included for illustration purposes. So here, as you can see, the bottom element This is the bottom element. This is a full entropy cone. Sorry, the full polyhedral cone. And the top element here, this is just the origins. And the way that I've labeled this, I've represented each of these in two ways. The first way is I've written it as the generators of these extreme rays. So each of these extreme rays is labeled by like to F14, for instance, is an extreme ray that is obtained by intersecting the plane 1 with plane 4. And I've color-coded the facets of this polyhedral cone in this way. So for instance, F14 is just, of course, the extreme ray that's generated at F14, and the yellow plane here, the yellow facet, it's generated by F12 and F14. So it's given here, it's generated by these two extreme rays. Now, the two ways that I'm representing them, one way I already mentioned is by labeling the extreme rays that generate the face. The other way I can label it is using these signed vectors. So these signed vectors, essentially what it's saying is it's a 0 if it lies on the face. Each of these components of the sign vector is indicating a particular hyperplane, a particular facet of the cone. So so it's a 0 if it lies on the facet, and it's a plus if it lies on the positive side of the facet. So of course here, for the yellow face here, it's a 0 on the first entry because it's the face, and then it lies on the positive side of these three faces. And similarly, if I look at, say, F14 here, the extreme ray here, it lies on the intersection of the first face and the fourth face, and then is on the positive side of the phase 2 and phase 3. So this is two ways that I can represent any polyhedral cone. And so here the join is the intersection of the faces. And if the meet is a little bit more technical, I can explain it if anyone is interested, but let me just leave it at that for the time being. Okay, so there is a lattice that is associated to the SA cone. And remember that the PMI, but what we're really interested in is studying the patterns of marginal independence. What are the PMIs that are realizable by a quantum state? So the PMIs are defined to be the linear span of the faces of the SA cone. And you might worry, well, it's not exactly the SA cone, so does it still have a lattice structure by reverse inclusion? And the answer is yes. In fact, one of the results that we prove in the paper is that there is an isomorphism between the SA cone lattice and the PMI lattice, both of which are ordered by reverse inclusion. And the PMI lattice, the meet between two PMIs is simply given to be the intersection of the vanishing MI instances. So if you hand me a PMI, I tell you which set I have the bipartition of into vanishing MI instances and positive MI instances. And so the P1 meet P2 is just specified by a new PMI, where the new PMI is has the vanishing MI instances that's given by the intersection of those found in P1 and P2. And notice that the number of MI instances that vanish is always going to be smaller because the intersection of the two sets of vanishing MI instances is always smaller. And so this means that the meet, as the greatest lower bound, as we move down in the lattice, the dimensionality of the PMI is actually increasing. And this is the reason why we ordered the lattice by reverse inclusion instead of inclusion. Does that make sense? Okay. Okay, so now let's move on to the object that we're really interested in, which is what we call the KC lattice. So what we really want to study is not all the PMIs, because many of these PMIs, they're not going to be realizable because they violate the Klein's condition. They are not KC compatible. So the subset of KC compatible PMIs in the lattice, it's a poset, but in general, it does not need to be a lattice because it's like if I just choose a random subset of a lattice, the meet and join of these elements may not exist because I may not have picked all the joins and meets of the subset. However, it turns out that the subset is a lattice, and the intuition behind this is the following. So suppose you hand me two KC compatible PMIs. This means that their sets of vanishing MI instances, they are downsets. And you can think of downsets sort of intuitively as kind of like being these like pyramids, because you can think of it, the top element is vanishing MI instance. It's saying that every MI instance that's less than or equal to it is also vanishing. So if I have two KC compatible PMIs, it's just saying, well, I'm just intersecting their downset is given by the intersection of their meet is given by the intersection of their downsets, and the intersection of these two pyramids is another pyramid. And so so that's intuition. Basically, the meet of any two KC compatible PMIs is another KC compatible PMI. And it is for this reason that the PMIs, they form the KC compatible ones. They also form a lattice. As a caveat, however, it is even though the KC lattice is a lattice, it is in general not a sublattice of the PMI lattice, because it is possible for elements in the KC lattice to have different join, even though they have the same meet. So that's just a caveat. Okay, so let's move on to the n equals 3 example. So let's do some explicit calculations. So for 3 qubits, this is a collection of KC compatible PMIs in a 7-dimensional entropy space. And here, what we did is that we labeled the dimensionality of the various PMIs from 0 to 7. So 0 is a trivial one, where I'm saying all the mutual informations are 0. And then 7 is the 7-dimensional one. It's a whole entropy space. I'm saying that I'm allowing for all the mutual information to be positive, and then I take the linear span of that. So as you can see, it is much more economical to look at just the KC compatible elements, because for dimensionality 3, 4, 5, it varies from like the number of elements in the KC compatible lattice. It varies from like 1/3 of the total PMIs to 1/5 of the total PMIs. So in terms of like running code to determine what are the faces in this subadditivity cone, it is much more efficient to just focus on the KC compatible ones. And we know how to describe them very efficiently. They are simply given by downsets of the MI pole set. So let's try to determine some of the properties of the n equals 3 KC lattice. So for the n equals 3 KC lattice, ideally, I will draw a Haas diagram involving all the elements, but it's very, now there's a lot of elements in the n equals 3 KC lattice. So instead, I'm going to draw this very schematic Haas diagram. So here, the top is the 0-dimensional PMI. So this is just the origin. And on the bottom, it's the full space. This is the full vector space. It's a 7-dimensional vector space. And here, these little dumbbells, these are represented by bell pairs. So for d equals 1, this is given by the extreme rays of the linear spans of the extreme rays of the subadditivity cone. And the linear, and these are just given by the various, the 6 bell pairs, because we have in n equals 3, so we have qubits A, B, and C, as well as purifier O. So, effectively, we have 4 qubits. So 4 choose 2 is equal to 6. So there's a total of 6 different bell pairs that we can choose. In each of those bell pairs, I can write down what their pattern of marginal independence is. So that corresponds to a particular extreme ray in the subadditivity cone. And this sort of cross here, this is what we call a perfect tensor. It's I can explain it if anyone is interested, but essentially, for all intents and purposes, you can think of this as being a multi-correlated quantum state where there's a multipartite correlation between all 4 parties at the same time. So I can then construct what we find is that we can then determine what are all the faces of the SA cone, like just by brute force. So d equals 2 is given by the linear span of any two of these extreme rays, any two Bell pairs, or including this perfect tensor. And similarly for three-dimensional faces, any triplet of these extreme rays will work. Once we reach 4 dimensions, then it turns out that there's some forbidden. It's not that you can just randomly take any 4 extreme rays. Any 4 extreme rays will not necessarily give you a 4-dimensional face in the SA cone. So these 4 Bell pairs and their permutations are forbidden. So anyways, this is the Haas diagram, the schematic Haas diagram for the n equals 3 KC compatible lattice. So every single PMI in this lattice is already by construction KC compatible. Now I've colored these certain elements in different colors. So the blue elements, these are what we call join irreducible elements. So these are elements that are not the join of any other elements. So of course, I would expect these elements to be join irreducible because these lie right on top of the bottom element. And so there's only one element here. So there's no way that any elements living in this layer can be the join of this element. But it is very interesting that in addition to these elements, there are these elements that are also join irreducible. They cannot be obtained by the join of any elements that live below it. And the green elements here, these are what we call the meet-irreducible elements. So they are not the meet of any elements. And of course, I expect these elements, which live just below the top element, to be meet-irreducible because there's only one element on top, so I cannot take the meet of any elements above it to get the elements in this layer. The reason why we want to focus on the join and meet-irreducible elements is because for instance, if I only knew the meet-irreducible elements and I know what the meet is, then I can just take the meet of all the pairs of these elements and then reconstruct the lattice constructively. So this is sort of like all I need, the essential information I need to reconstruct the entire lattice is either the meet-irreducible elements and what the meet is, or the join irreducible elements and what the join is. And this segues actually nicely into some terminology. So we say that atoms cover the bottom. So atoms are the elements that cover the bottom. In this example, these elements are the atoms, and the green elements over here, these are covered by the top. So these are what we call coatoms. So a lattice has a property, it's called atomistic, if every element is the join of the atoms. And similarly, as I just mentioned, coatoms, they are covered by the top, and a lattice is coatomistic if every element is a meet of the coatoms. So this means that just from essentially the definition, this is just the definition that a lattice is atomistic only if all its join irreducible elements are atoms. Because once you hand me the atoms, and then I can reconstruct all the other elements by just taking the join. And similarly, there's a dual statement, which is that lattice is coatomistic if only if all its meet-irreducible elements are coatoms. Okay, so it is clear that since there are join irreducible elements that are not atoms, in particular these elements, the n equals 3 KC lattice is not atomistic. However, it is coatomistic because all the meet-irreducible elements are the coatoms. So once you hand me the coatoms here and you hand me what the meet is, which we know is the intersection of the density sets, then I can reconstruct the entire lattice for you without having to like brute force find all of these by hand. Okay, so in lieu of time, I'm just going to quickly skim over this part, but basically, just to quickly describe, one of the very nice properties that lattices often have is that they satisfy the distributive law, which means that the meet and the join distributes inside the parentheses here. Now, unfortunately, the KC lattice, n equals 3 KC lattice, is not distributive, and so one might hope that perhaps, well, maybe there's it's not distributive, but there's a sort of a natural generalization of distributivity. It's a weaker notion called modularity. And so you might ask, well, is maybe the n equals 3 KC lattice is modular? Now, unfortunately, so modular lattices are the ones that obey the modular law, and you can quickly check that all distributive lattices, it satisfies this particular modular law. So this is a weaker condition than the distributive law. Now, I'm going to just quickly flash this, but basically we proved that the KC lattice is not modular because the existence of this sublattice inside it, and you can quickly check that this sublattice violates this modular law. It's just a very straightforward check. Now, there is a notion of a generalization to modularity called semi-modularity. So basically, just to summarize what we found that for n equals 3, the KC compatible lattice, it's not atomistic, it's not distributive, it's not modular, and then there's also this generalization of distributivity called joint semi-distributive, which I will not go into. However, it does satisfy some reasonable properties. So it is coatomistic, it is semi-modular, and it is meet semi-distributive. So the hope is that now at least a KC compatible lattice for n equals 3, it has these 3 nice properties. And so the question is whether or not these nice properties persist to larger n. Now, you might ask, well, what about these properties of the n equals 3 lattice that it doesn't have? Could it be that if I consider more qubits, that maybe the KC lattice will suddenly gain these properties? And unfortunately, the answer is no. Intuitively, the reason is because for n greater than 3 for larger n, the KC lattice will contain the n equals 3 KC lattice as a sublattice, because I can always just choose, like, say, if I have 7 qubits, I can always focus my attention on 3 of the 7 qubits, and those 3 qubits will form a KC lattice for n equals 3. So because it contains the n equals 3 KC lattice, basically, if these properties are not satisfied for the KC lattice, it's not satisfied for a sublattice of it. It also will not be satisfied for the larger lattice. The rigorous proof is given in our paper, and there's some subtleties that is involved. So it's not as easy as I made it sound, but roughly speaking, that's the general idea. There's some, it takes a little bit of work to make the proof rigorous, but this is an intuitive idea. Okay, so basically what we want to see is, do any of these nice properties extend to larger n? And the way that, of course, the natural thing to do is, well, can we redo our analysis for n equals 4? And the answer is yes, but it's starting to push on the limits of our computational abilities. And in fact, we had to use a few clever tricks in order to do this analysis. So for n equals 4, the KC compatible PMIs, they now live in a 15-dimensional entropy space because it's 2 to the 4 minus 1 dimensional. And now to illustrate the reason why we do not want to look at all PMIs, but only the KC compatible ones, because now here 0 through 15 is the dimensionality of the PMI. And you can see that if you want to look at all the PMIs, then we are hitting on the order of like the 7-dimensional ones. This is on the order of like, I think, 10 million. And these are all in the high millions of PMIs that we have to consider in general. But if we just focus ourselves to the KC compatible ones, they never exceed this. The 6-dimensional KC compatible PMIs is the largest, so it's around 6,000. So just from a computing standpoint, like, it is just much more efficient for us to focus our attention to just KC compatible PMIs. And we don't care about the general PMIs that do not satisfy the KC condition anyways, because those PMIs are going to violate SSA. Okay, so the n equals 4 KC lattice is very complicated. As I shown on the previous slide, there are several thousands of elements. Here we drew a very schematic Haas diagram for it. And so we omitted the d equals 0 top element and the d equals 15 bottom element, but we included everything in between. And again, we color-coded it where the blue elements are the join irreducible elements, and the green elements are the meet irreducible elements. Okay, so the n equals 4 KC lattice, then we can now check whether or not it obeys any of the nice properties that were obeyed in the n equals 3 lattice. And we proved that, unfortunately, every single nice property that the n equals 3 lattice have, the n equals 4 lattice does not have. And this is essentially the intuition behind why it has been so difficult for us to study entropy cones for n greater than or equal to 4. Like every single nice property that mathematicians have worked out for lattices in the last century, like all of the ones that we've been studying in the literature so far, they just fail for the n equals 4 KC compatible lattice. In addition to that, it also doesn't satisfy what is a technical condition known as a Jordan-Dedekind chain condition, which is a very intuitive property that we typically ascribe to lattices. Essentially, what it's saying is that if we have a pair of elements in the lattice, so we have, like, say, an element A and an element B, there could be many elements in between them. And the Jordan-Dedekind chain condition simply states that the number of jumps I need to go from the bottom element to the top element, it's the same regardless of which path I take. So there's a notion of levels within the lattice. And essentially the KC compatible lattice for n equals 4, it doesn't satisfy this condition. So it really loses all the nice properties. Now, of course, what we want to really do is we want to make general statements that is applicable to all n, not just for n equals 3 and n equals 4, because that would be a very restricted application. And of course, the way that we argue that is that it loses all these nice properties for larger n is the intuition I already explained earlier, which is that the larger lattice will always contain the n equals 4 KC lattice as a sublattice of it, and therefore it also fails to have any of these nice properties. And of course, like I said, it also doesn't satisfy Jordan-Dedekind chain condition, and all these negative results partially suggest why the entropy cone for general n has been so difficult to study. There are a few technical results that we also obtained that we proved, which does suggest that there's still some structure that are in the KC compatible lattices for arbitrary n, but I can't talk about those if anyone is interested, but they are rather technical results. And so I didn't include them in these slides, but I have auxiliary slides if people want to see. So let me just quickly summarize what we have talked about today. We began by introducing what Klein's condition is, which is an approximation to SSA, so that we don't have to introduce any new additional inequalities beyond subadditivity, but instead we are able to use this combinatoric constraint to restrict the number of PMIs that we need to consider that are potentially realizable by quantum states. We then explicitly constructed the KC-compatible PMI lattice for n equals 2, 3, and 4, and we proved various structural results concerning these lattices. And finally, we generalized our proof to the KC lattice for n greater than or equal to 4, and demonstrated that this lattice unfortunately does not have many nice properties, and nice being the ones that I alluded to in the several slides ago. So there's still a lot of ongoing research that is going on. So one of the things that I mentioned earlier is that if you tell me what the meet is and what are the meet irreducible elements, then I can fully reconstruct the lattice. I don't need to sort of construct the full lattice like by brute force. And we know what the meet is between these KC compatible PMIs. They're simply given by the intersection of the downsets. So the meet is very easy to describe. And so it really, all we need to do is figure out a clever way to determine what are the meet irreducible elements, and then we can fully construct the lattice. So this is something that we are currently working on, and it would be great if we can sort of just have a way of obtaining directly what the meet irreducible elements are. And from that, we can then, of course, we don't need to brute force construct the lattice every single time, because to do that, once for even small, like n equals 6, it is completely intractable by the algorithms that we have currently. Of course, another natural next step is to understand how well does the KC approximates SSA, because once we maybe KC is a very good approximation, or like it is even equivalent to SSA for certain subclasses of PMIs. So for n less than or equal to 5, actually, we proved that the KC compatible PMIs are exactly equivalent to the PMIs that are consistent with SSA for one-dimensional PMIs. We don't know what the result is in general, but it would be super nice if we can show that even for one-dimensional PMIs, and this will be already very interesting because the one-dimensional PMIs are essentially what generates the entire entropy column. If we can show that essentially the KC condition is exactly the same as SSA. So it would be very nice if we can have a quantitative statement for saying how well does KC approximates SSA. And so essentially solving either of these problems would really be a big step towards solving the quantum marginal independence problem. And from a higher perspective, of course, there's also holographic directions that we can explore to in terms of fixing what exactly the holographic entropy column is. So that is all I have. Yeah, and thank you very much for your time and attention.
Okay, thank you. It's a very nice talk. Thank you so much.
Thank you very much.
Yeah, sorry, let me see if I can see you guys again. Great. Yeah, so are there any questions?
Any questions from the audience?
I think one question that I have is that if you say if you want to, so let me first define this Markov state. So Markov state is the state that satisfies strong subadditivity inequalities, and this was proved given by Haydens and Winters. Say if I want to specify for example, in trace distance to the Markov state, say epsilon, would your method give us a constructed way of construct those approximate Markov state?
So that's a little bit, let's see. So the Markov state, it's already, because it's an explicit state, you can actually determine all the mutual information of the pairs already exactly, right? So in that case, I would say it's a little bit. I wouldn't know how to apply what we have been doing to like a specific state because it's not given by a pattern of marginal independence. The Markov state, I would say there's an approximate notion of it. If you tell me that you want a Markov state where only certain pairs of mutual informations is positive, so you don't specify exactly what the Markov state is, but you give me a class of Markov states. And then I can use this to rule out, well, which ones might be Markov and which ones are not. So, yeah. So basically, I can, if you hand me a pattern, I can tell you immediately whether or not by this KC condition that cannot be a Markov state. But I cannot tell you the fine, because what you're saying is you want the more fine-grained notion of exactly what is a Markov state, and this cannot do that. It can only it can use as an organizational principle to sort of classify Markov states. Yeah.
Okay, understood. Thank you.
Sorry, I have a stupid question.
Oh, yeah, please.
Yes, so in the definition of this entropy vector, so how do you define it?
So these are good. So these entropy vectors, yeah, so let me go. Yeah, let me go to this slide. Yeah. So yeah, so these entropy vectors, yeah, can you see this?
Yes.
Yeah, so basically it's a vector space, and so let's just look at 2 qubits, for instance. So if you hand me 2 qubits A and B, then I can tell you I can partial trace out A, or I can partial trace out B, and of course there's also given by the density matrix of AB, right? So there's three pieces of information that you need to tell me what is its entropy. You need to tell me the entropy of A, the entropy of B, and the entropy of AB. Right?
Mm-hmm.
Okay, so that specifies a point in entropy space, because every axis in this vector space is a entropy of a subset of the qubits. And so, for instance, if I'm 1, 1, 1 in this 3-dimensional vector space, what I'm telling you is that this state must have entropy of S of A is equal to 1, S of B is equal to 1, and S of AB is equal to 1.
Okay, so so my question is actually that since we are only using subadditivity, the inequalities or relations we wrote down are linear, basically. Yes. So are there any higher order relations we can input into this cone structure?
Oh yes, absolutely. So one thing that oftentimes so for instance, I alluded to these states called holographic states that high energy theorists are interested in. So these holographic states, they obey additional inequalities. These are inequalities that are not necessarily obeyed by quantum states, but they are obeyed by these holographic states. And so these are additional inequalities, and the holographic entropy cone would be essentially this subadditivity cone with all of these strong subadditivity, and then it has also, I don't know if you're familiar with this notion of topological entanglement. This was introduced by Kataev and Prescott, I think. But basically, these are additional entropy inequalities, and what you end up doing is your entropy cone, whatever you're interested in, is carved out by all of these additional inequalities as well. For the quantum entropy cone, for the holographic entropy cone, it's actually known that all the inequalities are linear. So it will always be, the entropy cone will always be polyhedral, and so it will be carved out by these half spaces. For the quantum cone, correct me if I'm wrong, but I actually think that it's not known that higher entropy inequalities have to be linear. Right. I think it is there's no proof that that has to be the case. Yes, if you have nonlinear inequalities, then this will cease to be a polyhedral cone, but it would in general still be a convex cone.
Mm-hmm. Okay, thank you.
Mm-hmm.
Maybe I ask some basic outsider questions. So you are trying to, your ultimate goal is to see the holographic construction. So you try to see the lattice construction, and you see how different particles are, to form the lattice, you want to see all the constraints. Is that right? Your ultimate goal.
Sorry. Are you asking how, like, is the ultimate goal? Sorry, I just couldn't hear very well. Is the ultimate goal, like you're saying, like how this lattice applies to the holographic construction?
Yes.
Yeah. So I actually didn't talk about this. So the reason why this will be useful for the holographic construction is because of this paper. And what this paper argued was that there is a way to essentially to construct the holographic entropy cone. Now we have to worry about many additional inequalities because these holographic states satisfy many more inequalities. But what this paper argued is that, say, to study, like, say, the holographic entropy cone, like if I want to study the entropy cone, like evolving, say, for n equals 5, for 5 states, I don't need any of the I don't need any of these additional inequalities as long as I study just a subadditivity column involving a larger number of parties. So for instance, what they're saying is that essentially all the information about the holographic entropy cone is actually contained, say for n equals 5, is contained in the subadditivity cone, say for n equals like 11 or something. So, and then of course, not every single element in the n equals 11 subadditivity cone will be in the holographic entropy cone. But I think the precise claim is that the extreme ray, a subset of the extreme rays in the n equals 11 subadditivity cone are precisely the extreme rays of the holographic entropy cone for n equals 5. And so in that sense, it's reduced the study of the holographic entropy cone to the study of the subadditivity cones for larger n. Now, of course, this is only useful if we know how to compute what the subadditivity cone is for much larger n. And like, you know, for n equals 5 holographic entropy cone, like you might need to go up to n equals 13. And that's just from a combinatoric standpoint, like completely out of reach right now. And so what we're trying to do using this lattice construction is try to find some order, some structure in constructing the subadditivity cone so that we can try to at least have some universal messages for arbitrarily large n. And of course, well, unfortunately, most of the results that we found is negative, but there's some positive results that we found as well and that we're hoping to exploit. For instance, we have a theorem in the paper that tells us like that classifies the joint irreducible elements in the KC lattice for arbitrary n. Now, unfortunately, the join is much more difficult to describe in the KC lattice than the meet. The meet, as I explained, is the intersection of the downsets of vanishing MI instances. The join does not have such a simple description. So what we really want is not just joint irreducible elements, but the meet irreducible elements. But the fact that there's some structure in the joint irreducible elements, like it gives us hope that, like, you know, if we work harder, there might be ways to like really whittle down what the subadditivity cone is, even for relatively large n, to the within the realm of computing, like things that like algorithms that we can use to like determine like what the KC compatible lattice is. And from there, then we can determine what how to constrain the holographic entropy cone.
I see. Thank you. Another question is that you try to deal with the subadditivity cone and then map to the mutual information and then map to lattice. And so you use this lattice because you want to make the convex product and for all those construction. What's the reason you do the combinatorial approach to deal with them?
Sorry, is the question what is the question that why did I do the combinatorial approach for?
Yeah, so I mean, you do not introduce new inequality, but you instead try to make different inequality, different combinatorial approach. What's the reason to do this?
Oh, I see. Yeah. So the reason what was this? Let's see. I had a slide on this. Here. Yeah. The reason is because if I include strong subadditivity as well, then it's actually I have to include many new inequalities. So if I, for instance, if I wanted to do the study for n equals 4, where there was like 10 million, dimension 7 PMIs, that would have been completely intractable if I included strong subadditivity as well, because strong subadditivity would have like, I now have to like, now the cone, I have like also to impose strong subadditivity and it's going to carve out many more faces. So that's one reason. The other reason is because right now the problem that we want to solve is the pattern, the quantum marginal independence problem, which is only sensitive to subadditivity. If I impose strong subadditivity, then many different faces of the strong subadditivity cone is going to correspond to the same PMI because they all going to satisfy the same subadditivity relations. It's just that they're going to differ in their saturation of the strong subadditivity. So for those two reasons, I did not include, I did not include strong subadditivity as an additional inequality, but rather we impose this combinatoric approach.
I see. Okay, thank you.
Mm-hmm.
Thank you very much. Okay, do we have any more questions for a speaker? I think there are not. So let's thank our speaker again. Thank you very much for coming here and giving us.
Yeah, thank you. Yeah, this was lots of fun.
Okay. Hope to see you soon. Bye.
Yeah, thank you. Okay, bye.
Bye.